So we move forward today to semi-final number 2 of the 2025 MIT Integration B. There were 4 problems in this semi-final. The first problem was the indefinite integral of the square root of the product of x to the power 6 plus 1 and x squared plus 1 all over x to the power 3. The second problem in that semi-final was the definite integral from x equals to 0 to x equals to 1 of the natural logarithm of x over the square root of x minus x squared. Problem number 3, a very interesting problem, and the definite integral from x equals to 1 to x tending to infinity of the inverse of the square of the summation from k equals to 0 to k tending to infinity of negative 1 to the power k times the maximum between 0 and x minus k. This is certainly an interesting problem. The last one is also another very interesting problem. A definite integral from x equals to 0 to x equals to 1 of the floor of the log to the base 2 of x minus 2 to the power the floor of log to the base 2 of x. Another very fascinating problem. So this is what we're going to be looking on at today. I hope you stay put. It's pretty extended. We're going to try and be more elaborate. This is not an exercise in seeing how fast we can solve this problem, but an exercise in decoding and seeing just interesting points that were being tested. So allowing you to maybe learn a trick or two on how to solve such problems. So without much ado, let's jump on to our problems. On to problem number 1. So this is obviously kind of, hard to decipher where to begin from. But my initial guess is to see if x to the power 6 plus 1 has x squared plus 1 as a factor. And so what I do is I would quickly go and do a long division. And so dividing x to the power 6 plus 1 by x squared plus 1 means I would have to multiply that by x to the power 4. That gives me x to the power 6 plus x to the power 4. Subtract that from x to the power 6 plus 1, and we get minus x to the power 4 plus 1. And then multiply by negative x squared, which we get negative x to the power 4 minus x squared. Subtract that from negative x to the power 4 plus 1. We get x squared plus 1. And then multiply this by 1. We get x squared plus 1. And that has no residue. So x to the power 6 plus 1 is the same as x to the power 4 minus x squared plus 1 times x squared plus 1. So I quickly come down and feed that into our integrand, and that means now under the square root sign we have x to the power 4 minus x squared plus 1 times x squared plus 1 squared. And that means now we can pull x squared plus 1 out so that this square disappears. The next thing we would want to do is separate x cubed into x squared times x, so that when that x goes under the square root sign, it becomes x squared. So as you can see, we have x squared here, which when it goes out, it becomes x. So x times x squared becomes x to the power 3 here. So what that means is that we have 1, x squared plus 1 divided by x squared is 1 plus 1 over x squared times the square root of x squared minus 1 plus 1 over x squared. So this results by dividing through by x squared under the square root sign. So let's rearrange a couple of things. this whatever is under the square root sign is the same as x minus 1 over x all squared plus 1. And that is easy to see because we have 1 over x squared here, which and then we have x squared here. And because when you do that, we have minus 2, but we have a minus 1, so we have to add an extra 1 here to cancel, to bring it back to minus 1 instead of the minus 2 that would result from squaring this. So, as you can see, this here is the derivative of whatever is inside the bracket here. So we can go ahead and say let u be equal to x minus 1 over x, such that du dx is the same as 1 plus x squared. And so du can be used to substitute the product of 1 plus x squared and dx as shown here. And so our integral now, this integral that has been rearranged into what we see here, is the same as, in place of the product of this and dx, we have du, and whatever is inside this bracket is u, so we have u squared. So it simplifies into this is a very simple integral. And for those of us who have the results of this in memory, this is the same as half times u times square root of u squared plus 1 plus the arc hyperbolic tangent of u over square root of u squared plus 1, or another way is just the same as half u times square root of u squared plus arc sine of u, arc hyperbolic sine of u. So we could use this right away, but and this is some of the things that you have to have in memory too, and it's quick for, if you have this in your memory, it's easy to access and use it. But if you don't know it, let's just maybe spend some time to prove that our integrals are as shown here. So let's say let p be equal to the square root of u squared plus 1, such that p squared is u squared plus 1, and so 2p dp du is equals to 2u, such that p over u dp du is equals to 1, and that means that p over u, which is so u here is from here is the square root of p squared minus 1. So this is p over square root of p squared minus 1 dp equals to du. So we can now substitute in place of square root of u squared plus 1, we have p. In place of du, we have p over square root of p squared minus 1 dp. And so we have the integral of p squared over square root of p squared minus 1. Let's continue and see how we might do that. The quickest substitution is the hyperbolic sign. So let's see how we might be able to do that. So having this as our integral, we can rearrange it a little bit so that it's easy. So this is the same as p squared minus 1 plus 1. And so p squared minus 1 divided by square root of p squared minus 1 is the same as square root of p squared minus 1. And then we have 1 over square root of p squared minus 1, so that when we say let p be equal to the hyperbolic cosine, that would be easier. So dp dy, so let p be equal to hyperbolic cosine of y means that dp dy is hyperbolic sine of y. And that means that now we can say that p can be substituted off by hyperbolic sine of y dy. And that's what we've done here. And this simplifies to hyperbolic sine of y plus 1 over hyperbolic sine of y times hyperbolic sine of y dy. And that is hyperbolic sine squared y plus 1, and we can re-express this hyperbolic sine squared y into hyperbolic cosine 2y minus 1 over 2 plus 1, And that means that now we can reduce this into half hyperbolic cosine 2y plus a half, right? So this minus half plus 1 is half here. And when we integrate, this becomes a quarter hyperbolic sine 2y plus half of y plus the integration constant c. And we could say, okay, the sine 2y is the same as 2 sine y cos 2 hyperbolic sine y cosine hyperbolic cosine y, and hyperbolic sine y is the same as square root of hyperbolic cosine squared y minus 1. And so we can go ahead and say, since we had said that p is equals to the hyperbolic cosine of y, it means that now here we have half p squared minus 1 times p plus half the arc hyperbolic cosine of p plus c. Interestingly, since we had also said p is equals to u squared plus 1 and p squared is equals to u squared plus 1, it means that now we have half p squared minus 1 is u squared, square root is u, and then p here is the same as square root of u squared. So we have half u times square root of u squared plus 1 plus the half a cosine, hyperbolic cosine of square root of u squared plus 1. Now we can simplify this part here. It's easy to see how to simplify that. Since we have half the u times square root of u squared plus 1 plus half arc hyperbolic cosine of u squared, square root of u squared plus 1. We know that let's go and say cos squared x minus sinh squared x is equals to 1, which means that sinh squared x is equals to cos squared x minus 1, right? And so if we have y to be equal to cos square root of u squared plus 1, that means that cos y is equals to u squared plus 1, and so cos squared is equals to u squared plus 1, and so sinh squared y is equals to u squared, and therefore y is equals to arc sinh of u. And so we can now replace this, or we can use half arc sinh of u instead. But also it's easy to see that since tangent of y is going to be sinh of y over cos of y, which is equals to obviously u over square root of u squared plus 1. Y is also going to be equal to the arc tangent, hyperbolic tangent of u over square root of u squared plus 1. So we could also put this as half u times square root of u squared plus 1 plus half arc hyperbolic tangent of u over square root of u squared plus 1. And so we've proved whatever we wanted to prove. But then if we go back to our original integral here, and we had said that is the same as the square root integral of square root of u squared plus 1, where u is equals to x minus 1, and we had found that this is the same as half u square root of u squared plus 1 plus a half arc hyperbolic tangent or u over u squared plus 1. We can now feed in place of u, we can put x minus 1 over x, and here the same, wherever you see u, we feed in the x minus 1 over x, right? And then next thing is just to simplify and see what we get. All right. So we have half x minus 1 over x, and then when you square everything, we get x to the power 4 minus x squared plus 1 over x squared, half arctangent x minus 1 over x, x to the power 4, and then we get the square root of this x squared, and it goes up. Here at the same time, this x goes out, so we have x minus 1 over x times 1 over x times the square root of x to the power 4 minus x squared plus 1 here, and this can multiply across, and this one, when it went out, it now goes up here, and so we have half x going through, we have 1 minus 1 over x squared times the square root of x to the power 4 minus x squared plus 1 plus the arctangent of x squared minus 1 over x to the power 4 minus x squared plus 1 plus the integration constant. So on to the second problem. The integral from x equals to 0 to x equals to 1 of the natural logarithm of x over the square root of x minus x squared. I think the quickest thing one would want to do is it's counterintuitive, so I pull out the minus so that the x squared kind of comes first under the square root sign. And then what happens here is that this is the same as a quarter minus x minus a half squared. And that is for the single reason that we can now substitute this. We can just say let x minus a half be equal to a half sine theta, so that when we square this, there's a constant a quarter here, and we can factor the quarter out and get the square root of it, and then we have 1 minus sine squared theta, and then we can rationalize the denominator in some fashion. But anyway, let's get the derivative. So dx d theta is the same as half cosine theta, and that means that we can substitute dx with half cosine theta d theta. And then the limits, we can work the limit when x equals to 0. So negative a half equals to a half sine theta, means that we have negative 1 is equals to sine theta. The arc negative 1 is the same as negative pi over 2. And then when x equals to 1, 1 minus a half is a half, half divided by half. So sine theta equals to 1, and so arc of 1 is arc sine of 1 is pi over 2. So integral now becomes as follows. Integral is as follows. In place of x, we have half plus a half sine theta, and in place of x minus half, we're going to have a quarter. We're going to have a half sine theta, right? And then the limits, negative pi over 2 to pi over 2. Okay, so and then dx is half cosine theta. So we can now pull out the quarter out of the square root sign, and we'll get a half. And also up here we can factor out half, so this half here and this half here can interact, and then we're going to get cosine squared theta here. Square root of cosine squared, the square root of cosine squared theta is going to be cosine theta, and that will interact with that. So eventually we are going to have a very straightforward expression. But before that, let's just write everything down. So we have half cosine theta here, and we have a half cosine theta. And this divide with one another so that we no longer have a fraction, right? So we have now an integral from theta equals to negative pi over 2 to theta equals to pi over 2 of the natural log of half times 1 plus sine theta. Using the rules of logarithm now, we can, write this as log half plus log of 1 plus sine theta. And then again, this is same as 2 to the power negative 1, so we can pull out the negative 1 to this side. And so we have a nice integral from theta is equals to pi to negative, from theta equals to negative pi over 2 to pi over 2 of negative of natural log of 2 plus the log of 1 plus sine theta. And so this is a constant. We can quickly simplify that into negative log 2x with the limits applied appropriately, plus the integral from theta equals to pi over 2 to pi over 2 to theta equals to pi over 2 of natural log of 1 plus sine theta. And so here we have negative log 2 pi over 2 minus pi over 2 plus the same integral here. And so this is same as pi over 2 plus pi over 2, which is pi. So we have negative pi times log 2 plus this integral here. So let's continue. We can now then split this integral into the integral from negative pi over 2 to 0, and then from 0 to pi over 2, right? That's allowed. And so we have negative pi over 2, negative pi times log 2, and we have pi over 2 to 0. And here we've just flipped the sign so that the d theta here now becomes negative d theta, and then the theta in here propagates out, so we have 1 minus sine theta, and then the limit, obviously, the negative pi over 2 becomes pi over 2. So since we have a negative here, this allows us now to flip the limits. So we have negative pi log 2, and we have plus 0 to pi over 2 log of 1 minus sine theta. Now we can now add back, because the limits are the same, but the signs here are flipped. So we can add them together, and so that allows us to now multiply them under the log function, and that becomes using the difference of two squares, this becomes the log of 1 minus sine squared theta. And 1 minus sine squared theta becomes cosine squared theta, and the two can, in the square position here, goes out, and so we have the integral of so we have twice the integral from 0 to pi over 2 of natural log of cosine theta. Now this is a famous integral. It's actually negative pi over 2. The blue integral here is the same as negative pi over 2 log 2, but let's see how we may be able to actually get it to be that way, okay? So the first thing I think we may want to do is we would just say let theta be equals to pi over 2 minus u. such that d theta du is -1, and so d theta becomes negative du. So we can substitute d theta with negative du. So let's see how we may use that to move things around. Since we had said that theta is equals to pi over 2 minus u, that means u is the same as pi over 2 minus theta. So when theta is 0, pi over 2 minus 0 is pi over 2 positive. When theta is pi over 2, u is pi over 2 minus pi over 2, which is 0. And then negative du, the negative, we decided to put the negative here, and cosine pi over 2 minus u, that is cosine pi over 2 cosine u, plus sine pi over 2 sine u, so this becomes sine u, okay? And so we have this negative sign that allows us to flip the limits appropriately. So if we say that our integral is I being equal to the integral from 0 to pi over 2 of log cosine theta, that's the same as the integral from 0 to pi over 2 of log of sine theta from this expression here. So this is the same as this, right? And that means that twice of this is the same as the same integral from 0 to pi over 2 of log cosine theta plus 0 to pi over 2 log sine theta. Now adding them together means that we can now multiply cosine theta and sine theta. So we have log of a half sine 2 theta, right? And then now we can separate that so that we have log half plus log sine 2 theta, and that's the same as negative log 2. Negative log 2 can be integrated separately, and then log sine 2 theta can also be integrated separately. And so that becomes negative log 2 x 0 to pi over 2, and that is obviously minus pi over 2 log 2. That's easy to see. And then we have now a green integral here that will allow us to see that if we let y be equal to 2 theta, dy d theta being equal to 2 means that half dy is equal to d theta. And so fixing that in there, we have half the integral from 0 to, because we said y is 2 theta, so the limits become pi temporarily, and then that also means we can split this integral from 0 to pi over 2, and then from pi over 2 to pi, and that can allow us to see that this half log of sine of y plus half, we can subtract pi over 2, and so we have sine y minus pi over 2. This becomes cosine y, right? And so since we already know that these are the same integral, that becomes half times 2 log sine y and so this is the same as I. So back to our integral here, the 2I we had originally here means that we have a hidden I here. And so we can subtract I from both sides. So I is equals to negative a half log 2. And this is what we wanted to prove all along. But it's a popular integral that one needs to just have in mind, and it should be easily accessible when you're dealing with it. So our original integral had come to negative pi log 2 plus twice the blue integral, and we wanted to prove that this is the same as this. So we're just going to plug this here. So we're going to have minus pi log 2 plus twice minus half pi over 2 log 2, and that is the same as twice of pi log 2, and that is the answer that was being sought for. A little bit windy, but we just wanted to be thorough. If you have any questions, please reach us through the comment section, or you can reach us via email, and we'll be able to help in answering any questions that you may have. On to problem number 3. This is certainly a very interesting problem. A definite integral from x equals to 1 to x tending to infinity of the inverse of the square of the summation from k equals to 0 to k tending to infinity of negative 1 to the k times the maximum between either 0 or x minus k. So this is interesting. Now, what is this complex stuff under the these brackets? This is interesting. So let's divide, and I think it's always good to just see what is happening. This suddenly we have the x-axis and it spans all the way from 1 to infinity, but I just took the first 11. I'm not even going to use all the 11, but we just want to see the progression of things so that we draw an inference from what is happening here. So between 1 and 2, right? So what is happening there? It means that the summation is from k equals 0 to infinity of negative 1 to the k max 0 k minus 1. When k equals to 0, we have negative 1 to the 0 maximum between 0 and x, plus when k equals to 1, negative 1 plus to the power 1 maximum between 0 and x minus 1. Why have we ignored the rest? Because between here x minus 2 is less than 0, so it all becomes just 0. Okay, so here this becomes obviously x, because x here is greater than 0, so it becomes x. And then here as well, because the value here is greater than 1, so we have first of all here negative 1 to the 1 is negative 1 times x minus 1. So x minus 1 is still greater than 0, so we can pull that out. And so we get x minus x plus 1, so we get plus 1, right? So this becomes 1 over 1 squared. So that is what we see in the interval 1 to 2. What about when we go to 2 to 3, right? What happens there? It means that then the summation becomes we have the 0, obviously, negative 1 to the 0, maximum 0, and x, and then negative 1 to the 1, maximum between 0 and x minus 1. And then we still have to go up to 2 because x minus 2 is still greater than 0 in this interval. So we can pull out that. And then the rest will just fall out as 0. So we have x minus x minus 1 plus. So this becomes plus because we have a square here. And so we have x minus 1 plus x minus 2. and that becomes x minus x is obviously 0, and then plus 1, this negative and this negative 1, so we have plus 1, and 1 plus x minus 2 becomes x minus 1. So in this interval we have 1 over x minus 1 squared. So this entire summation reciprocal square, the reciprocal of the square of the summation is what we're looking at here. And then we go on to the third portion. We continue, and this goes up to 3, but obviously there's a negative 1 here, so you add all this and we get 2. So in this interval we have 1 over 2 squared. Let's go to interval between 4 and 5. Here we get, it goes all the way up to x minus 4. And there is a positive here because we have to the power 4 here, and then when you add things we get x minus 2 squared, right? So we have 1 over x minus 2 squared. And so we continue, and that is 3 squared. This is x minus 3 squared, and then we have between 7 and 8 we have 1 over 4 squared, and between 8 and 9 we have x minus 4 squared. So that is actually what our integral is all about. So what we go ahead and do is we're just going to have integral between 1 and 2, between 2 and 3, between 3 and 4, 4 and 5, and we fit in. Now we see this is a constant here, this is a constant here, so I have decided to color the constants in blue so that the integral is straightforward, where we just pull out, and since the difference between the limits is just 1, those things can be pulled out, and so we have a summation of 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared all the way to infinity, and then we have the actual integral now of 1 over x minus 1 squared in the interval 2 to 3, and then 1 over x minus 2 squared in the interval 4 to 5, and then x minus 3 squared in the interval 6 to 7, and so on. Now this first summation here is what we call the Bezo problem. So those will just add up to pi squared over 6. If you don't know what a Bezo problem is, please, you could just go online and see what that means. But integrating these other special integrals here means that we have negative 1 over x minus 1 in this interval, negative 1 over x minus 2 in this interval, and then when you subtract now you begin to see that here because of the negative we begin with the lower side, so we have 1 over 2 minus 1 is 1 over 1 minus 1 over 3 minus 1, which is 1 over 2, and so on. So we begin to see that this is a telescoping series because this and this cancel, this and this cancel, this, and all the way into infinity, and we are only left with 1 here. So our integral becomes pi squared over 6 plus 1. And that is the answer that was being sought for. Certainly, the one of the hardest problem that people had to contend with in this tournament. That's problem number 4. A definite integral from x equals to 0 to x equals to 1 with the floor of log to the base 2 of x to the power 2 to the power log to the base 2 of x. So the first question would ask us of what is the floor? What is the floor function? So the floor of the function fx is equals to k when fx is greater or equal to k and less than k plus 1. So it is that function that extracts the integer portion of a function, and it takes out the integer less than a function. So let's begin by looking at log 2 of x, log to the base 2 of x. So it crosses 0 at point 1, and so the floor function here would be these discrete points that we extracted, which is interesting. So how do we proceed from here? So that means that in the interval 2 to the power negative k plus 1 and 2 to the power negative k, in that interval, the value we are looking at here is negative k plus 1. That is the integer value lower than log 2x, right? So that means that now our integral here becomes a summation of the different strips that we have, and between the strip between x is equal to 2 to the power negative k plus 1 and x equals to 2 to the power negative k, we're going to have the floor of log 2 to the log 2 of x minus 2 to the power negative k plus 1, right? So that we've reduced it up to there, but still we do have this floor function, right? And so within this interval, we can still divide that into strips that afford us, in each strip, we're going to have log 2 of x minus 2 to the power negative k plus 1, providing us a function from negative infinity here all the way to negative k plus 1, because at this point is when x is equals to 2 to the power negative k and log of to the base 2 of 2 to the power negative k minus 2 to the power negative k plus 1 gives us log to the power log of the base 2 of 2 to the power negative k plus 1, which is k negative k plus 1. But when x is 2 to the power negative k plus 1, here that is the same as this becomes 0, and so everything tends to infinity. So between this interval here we have log to the base 2 of x minus 2 to the power negative k plus 1 behaving in this format. And so when we discretize it using the flow, so we have these discrete functions here, and that means that now we can we're going to have another summation sandwiched another summation inside this summation sign. So we have x is equals to 2 to the power negative k plus 1 to x is equals to 2 to the power negative k in that interval, and we have log to the base 2 of x minus 2 to the power negative k plus 1. In this interval we have strips, and we see that we have the strips, and in each strip we have a constant value attributable to the flow of this function, right? So we have this, and so we have now rectangles that we can just add up, and we see that the width and the height is obviously a negative value lower than for example, for this is going to be negative k plus 2, because that's the integer lower than negative k plus 1. And so on and so on and so on. So our flow is going to be that. Now let's focus in this interval here when log to the base 2 x minus 2 to the power negative k plus 1 flow is equals to negative k plus 2. In this interval, it means that this function lies between negative k plus 2 and negative k plus 1. It lies between this and this. And that means that the function now x minus 2 to the power negative k plus 1 is between 2 to the power. We've just taken the power of 2 on both sides. Is greater or equal to 2 to the power negative k plus 2, and less than 2 to the power k plus 1, the power negative k plus 1. And then we can add both sides with this. So we have 2 to the power negative k plus 1 plus 2 to the power negative k plus 2 on the lower side. On the upper side, we have 2 to the power negative k plus 1 plus 2 to the power negative k plus 1 on the upper side. And so this becomes 3 times 2 to the power negative k plus 2 on the lower side. On the upper side, we have 4 times 2 to the power negative k plus 2. And if we take this to be our L, this is because the width is k plus 2 negative. And so in terms of if we take this to be our index L, so this can be 3 times 2 to the power negative L on the lower side. On the upper side, we have 4 times 2 to the power negative L. So the interval, the difference here is the same as 2 to the power negative L. So what that means is that this integral of ours becomes, okay, we are summing between different strips, and in each strip or kth strip we have it beginning from L is equals to k plus 2. So we saw it began from negative k plus 2 all the way to infinity. So we choose to use the positive on the index, but on the actual value we've attached a negative sign. So from L is equals to k plus 2 to infinity, and in there we saw the integral when at each L we have 3 times 2 to the power negative L to 4 times 2 to the power negative L, and the height is L. We take the height to be L. Okay, so that means that we can integrate it, and so that becomes negative L times 4 times 2 to the power negative L minus 3 times 2 to the power negative L. And so that becomes the summation from k equals to 0 to infinity of the sum from L equals to k plus 2 to infinity of negative L times 2 to the power negative L, which is the same as, we pull the negative sign out, which is the same as L over 2 to the L. So we want to find that, and that we begin with our geometric progression, and we know this from k equals 0 to n of a to the x to the power k. That's the same as a times 1 plus x to the power n plus 1 over 1 minus x. And so that the derivative of that, since the zeroth value is a constant, so that value disappears, so we begin from k equals to 1, and so the k goes down, so we have ak times x at the power k minus 1 times the derivative of this, and that becomes what we see here. Rearranging it in a best way, that just leads us to what we have here. Then we multiply x to both sides, so we have the summation of akx to the power k is the same as a times negative n plus 1 x to the power n plus 1 plus nx to the power n plus 2 plus x over 1 minus x to the power 2. This is just, you can ignore this part, but this is something that obviously one needs to know. When x is equals to a half and a equals to 1, that means that our problem from k equals to 1 to n of k over to the power k is what we have here, and that simplifies to 2 minus n plus 1 over 2 to the power n minus 1 plus 2 to the power, n plus n to the power 2 to the power n, which simplifies to 2 minus n plus 2 over 2 to the n. So this is a formula that one ought to have known. But using that now, for what we have here, we see that we have the summation to infinity minus the summation up to k plus 1. So the summation to infinity is going to be a half, because the constant ratio here is 1 over 2, so a half over 1 minus a half squared minus that sum to k plus 1 is 2, k plus 1 plus 2 over 2 to the power k plus 1. And that simplifies to what we have here, which is k plus 3 over 2 to the power k plus 1. And remember, we do have the negative sign out, right? So we continue, and we do have two summations, k over 2 to the power k and 3 over 2 to the power k. This is a geometric progression, and this is a progression where we have a mixture of the arithmetic and the geometric. And so here, because we are summing from 0 to infinity, we have 1 over 2 over 1 minus a half squared, and then plus 3, common ratio half, 1 over 1 minus 3 over 2, 1 over 1 minus 1 over 2, which is going to be a half. So we have a half over 1 minus a half is going to be a half squared, which is 1 over 4. And then here we have 3 times 1 over 1 over 2, 1 over 1 over 2. And so that becomes, taking this 2 squared out, we have 2 squared times a half, which becomes 2. And then 3, this becomes 3 times 2, which is 6. So 2 plus 6, and we pulled a half out, so negative a half times 8 is what we're going to have, and that means the answer is negative 4. So that was a little bit windy, but all the same, we decided to take the long route of deriving things. I hope you do enjoy following through. If you have any questions, feel free to reach out to us. We'd be glad to explain anything that you'd be interested in. So until next time, be blessed, and it was an absolute pleasure hanging out with you.